Okay, so let's look at the path of light into the eye. And the main idea here is that most of the diffraction occurs when light enters into the cornea. So as the light enters in, most of the refraction, excuse me, is going to occur right here. And then it's going to go through the lens, which is, inside of the cornea. And then that will further focus the light onto the retina. So the lens is really, you can just think of it like a fine tuner for the light, but most of the refraction, most of the bending of light occurs at the air cornea interface, because at that point, that's where the indices of refraction are more different or disparate. So remember this equation for the law of refraction, n1 sine theta 1 equals n2 sine theta 2. If these two are really close to one another, then these refraction angles, the angles that the light bends, is also going to be really similar. So you want your indices of refraction to be different, that if they're not that different, then the light will just continue on straight. But if you have indices of refraction that are really different, then the light will bend more. Also, just sort of for your information, the index of refraction for the aqueous and vitreous humor is basically that of water. And in fact, it's mostly water, those materials. Uh, just as an aside, you can measure the index of refraction to determine unknown materials, and that's a pretty common way to, if you have a liquid or a gas, you can measure what is the angle that light refracts when it travels into that material, and then that gives you a measure for its index of refraction for this value n, and you can look that up in tabulated values to find out what is that material. Let's look at the comparison of the eye with a camera. So with a camera, you change the image distance. Oops. For different object distances. So if I have a camera with a lens like this, my image distance is this distance, di, and my object distance is this distance, do, to wherever my subject is. And I want to have a camera such that I can take different object distances. And when I change the object distance, then this distance will increase or decrease. And so the camera lens can either move in or it can move out. Now, with your phone camera, it doesn't do that. I think some of the fanciest phones do, like maybe the iPhone 11 might have an actual lens that can zoom. Most those do a software zoom, so it's a little bit different. But for a normal camera, you actually move the lens back and forth. With the eye, however, you can't change the image distance because with an eye, the image distance is going to be the distance between where the lens is and where the retina is. And so DI is fixed. You can't move the retina around. So with the eye, instead of changing the image distance, when you have different object distances, then you have to change the focal length. So with the eye, you change the focal length. Let's think about if I have an object that's far away. We're going to do a little ray diagram tracing. There are just a few simple rules with ray diagrams. Actually, really just one rule that I want you to know, that a parallel ray goes through the focal point. In fact, we've seen that. That's how we define focal point. If you take some of my other classes, we look at some of the additional rules. But imagine that my focal point is here and here. And then I have an object that's really far away. And when an object is really far away, the rays coming into the eye are going to be parallel, right? And so those rays, if they're parallel, will go through the focal point. But an image is formed where two rays cross. So instead of our focal point being there, we want our focal point to be at a position on the back of the retina. So when I'm looking at an object far away, if DO is really big, so that those rays are parallel, then the focal length of the lens will be equal to the image distance, and vice versa. The image distance is equal to the focal length. But if I'm looking at something close, there's my eye. Say that my subject is right here. I'm going to draw some rays that come from the guy, and then they will go down like that. Now, let me go ahead and tell you that the focal point is going to be smaller. So I'm going to draw one set of rays right there, because these rays, they aren't going to be parallel when they reach the eye. So I'm going to draw rays that look like this. These rays, I have to follow this rule that parallel ray goes through the focal point. So here's a ray that's coming along and it goes through the focal point. And then this is just the reverse of that rule. I have a ray that goes through the focal point and then it travels parallel to the axis of the lens. Okay, so these are two rays that I've drawn using this rule. Parallel ray goes through the focal point. Ray number one goes parallel here, and then it goes through the focal point, and then this one goes through the focal point and parallel to the axis. And they cross back here. Now, because they cross below the axis of the lens, and this would be the axis of the lens, sort of that center line, my image is going to be upside down like that. And that's just a fact of your eye, that the image in your eye is always upside down. In fact, you can buy glasses. Well, let me tell you. So the image of your eye is always upside down, and your brain takes that image and flips it right side up so that it makes sense to you. But you can buy these glasses that take everything that you see and they flip it upside down. I'll add a link for those in case you want to buy them. So when you put them on, everything just looks upside down. But then after a while, as you're wearing those glasses, everything gets flipped right side up again because your brain accounts for this, like, whoa, this isn't right, and flips that image right side up. Your brain is actually pretty remarkable at knowing what is reasonable and what's not reasonable, and it says an upside down image just isn't a reasonable thing. So eye is different from a camera in that way that the focal length can change. That when I'm looking at objects really far away, the focal length is equal to the image distance. And when I'm looking at objects that are closer, the focal length is less than the image distance. The focal length will never be bigger than the image distance because well, it'll just never be bigger than the image distance. Okay. I have a couple of videos. One addresses this idea, which is better, your eye or a camera, which is just better at detecting images and creating images. There's a great Physics Girl video, and then I'll also add a link to the glasses.